Hello guys, today we're going to be doing further mathematics paper 4 further statistics of the October-November series of 2020, the variant 4.1, which has the same paper as 4.3. So let's get right into it. Okay, so the first question is inferential statistics. Kayla is investigating the lengths of the leaves of a certain type of tree found in two forests X and Y. She chooses a random sample of 40 leaves of this type of forest of X and records the lengths in X centimeter. She also records the length Y centimeter for a random sample of 60 leaves of this type of forest of Y. Her results are summarized. Find the 90% confidence interval for the difference between the population means of length of leaves X and Y. Okay, so there is a formula to calculate the confidence interval, but before that we need to write down certain values. So number of X terms equals to 40 and number of Y terms is equal to 60, and therefore we can find out that our sample mean X mean is equal to the sum of all the X values divided by the number of X values, which is going to be 6.05. And using the same logic we can calculate the sample mean for Y, which is equal to total sum of all the Y values is 373.2, and we whole divide this by the number of terms of Y, which is 60. Okay, so we get the value 6.22. Okay, yes, now that we've calculated the basic values that we need to begin our calculations, we can write our formula. So the formula here is CI, which represents confidence interval, is equal to mean X minus mean Y, brackets, and then write plus or minus. Now we either write ZS or we write TS. Okay, and S is just basically the root of S2. Okay, so what do we write, Z or TS? Looking on the number of terms, we have here 40 terms for X, 60 terms for Y, and so the degrees of freedom would be 40 plus 60 minus 2, which is equal to 98. And in the statistical table you can see there are no critical values for 98 for T distribution. So we need to use this right here. That means we stick to ZS. Okay, but now that we have ZS, I want to directly plug in our values. So instead of writing ZS, I'm going to be writing root of S2. Okay, this will just make plugging in the values all the more easier. Okay, moving on, we have the sample mean X. So let's plug in the values we already know. Sample mean X minus sample mean Y, which is 6.05 minus 6.22, negative 0.17. Okay, and this is plus or minus with a particular Z value. So which Z value do we use? Well, over here we need to find the value for P. So how do we find the value for P? We take 90% confidence interval and plug it into the common equation, or we could just do 90% and convert it to decimal. We get 0.9, and then we look at 1, okay, which is the maximum probability, and we look what's right in between, which is 0.95. So we look at 0.95, we get the critical value as 1.645, and so we get 1.645 over here, and we multiply that with the root of S2. What do we find as S2? Well, this is where the calculation comes into play. So to find S2 when we have a two sample test, first we have to find S2 of x. So let's find S2 x here. S2 of x is equal to 1 divided by number of terms of x minus 1 multiplied by sum of all x squared values, subtract that with sum of x the whole squared whole divided by number of terms of x, and this will give us a value of, well, now we just need to plug this in our calculator. We have here 40 minus 1 multiplied by sum of x squared is 1587 minus it with sum of x the whole squared, so sum of x whole squared 242 whole squared divided by 40, and this is what we get when you plug in our answer, our values. We get 1229 whole divided by 390, and this, even though we're going to use this values, Cambridge expects us in the decimal form, so we can keep it to like 4 significant figures, so 3.151. we can keep it to these many significant figures. If you want, you can go more, they won't test you based on that. Okay, next we need to find S2y. S2y uses the same logic except we use different values. So S2y equals to 1 by number of terms of y minus 1, and we whole multiply this with sum of y squared, which is 2532.6, and we subtract that with our sum y whole squared, so 373.2 whole squared, and then we whole divide that with the number of y terms we have, so ny, and yes, that is our equation. Oh wait, but I've substituted the values in. So yeah, if you're going to write the general form, it's going to be sum of y squared, and we're going to write here in brackets sum of y. Yeah, this is the general equation. I have accidentally plugged in the actual values in the middle of writing the equation. Although they may not require this, it's suggested that you write the equation down, or at least plug in the values in places of these equations. 60 minus 1 and 1587 changes into, so what's square, it's 2532.6, and then we whole square the sum of y's, which is 373.2, whole divided with number of terms of y, which is 60, and this is equal to 3.5812.13 actually, but we can keep it at these many significant figures. Okay, notice how we didn't have a fraction value. That is because this value is a bit too great. So we can break down our equation into 1 by 59 multiplied by what's inside this bracket. So let's just calculate the value inside the bracket, which is 2532.6 minus sum y the whole squared, which is 373.2 the whole squared, whole divided by number of terms of y, which is 60. We get our fractional form 26412 whole divided by 125. We get what's inside the bracket, and we just multiply by that with 1 by 59. So if you multiply this answer with 1 by 59, you'll only get the decimal based answer. You're not going to get the fraction. Reason being that it's too complex. So when you're multiplying 26412 by 125 times 1 by 59, all we need to do is multiply the denominators. So 59 times 125 is equal to 7375. Therefore our 3.581 is also known as 26412 whole divided by 7375. This is our fractional value. The reason I say this is so important is because S2 is needed to use to calculate the confidence interval, and to find S2 we need accurate values. Even if we could use the answer function, it's best that you represent both your answers in decimal and fraction. Okay, moving on. Now we need to find S2, and S2 is given by the equation. Okay, first of all, we don't use S2P. That is because it doesn't say anywhere that the population variances are equal. If they were, we would use S2P. In this case, we don't. And so we use the basic formula S2x divided by number of terms of x plus S2y whole divided by number of terms of y, which is equal to, now here we can just plug in our decimal values, but I suggest using fractions. Yes, let's do 1229 by 390, and when you're dividing S2 of x, you're just multiplying the denominator of S2x with an x. That basically means 390 times 40, and this is added with, using the same logic, S2y will be 26412 whole divided by 7375 multiplied by 60, and this value gives us 0.13847. 3847. Okay, now that we have S2, we can plug in all our values into the final equation. So we get 0.17 plus or minus 1.645 root of 0.13847. And now let's just calculate this part of the answer. So we get next step, we get this negative 0.17 plus or minus this one. This we need to square, right? This was our answer before. We need to first root this answer and then times it with 1.645. We get 0.612 1 2. Keep it to 3 significance, right? Okay, now in most of the times I always say that whenever we're writing confidence intervals, we write in the format negative comma positive. Once again, I will specify that negative comma positive. This doesn't mean that our first value should be negative and the second value should be positive. It means that the result of this plus or minus, okay, if when you use minus instead of the plus, you will get an answer, and when you get that answer, that will be the first value here. Then in the plus or minus, when you use the plus sign, you will get the next value, which is going to be the second value in your bracket. So when you do with minus, you get negative 0.17 minus 0.612, and so you get, you can plug this in our calculator, minus answer, which is equal to the negative 0.782. Right, and now we can just get back our value, okay, this right here. And now let's see what happens if we add negative 0.17 with positive 6.12. What will our value become? This added with negative 0.17 is equal to 0.442. Right, so now that we have our negative operation done first, that's our first value of the confidence interval. CI is equal to negative 0.782 comma the positive operations result, which is 0.442, and you close that with brackets, and that sums up the first question, right? Moving on, before we finish this question entirely, I do want to note that whenever they give two sample tests for confidence intervals, you should know that sometimes they look at the modulus of x minus y. Sample means difference. They look at the modulus, and then they will get a positive value for this negative 0.17. And then when you do the plus or minus equations, you will get the positives, you'll get a different value of sorts. But they permit both ways. You don't need to plug this one in, right? You can do this. It's completely optional though. Okay, moving on, we go to the second question. Metal rods produced by a certain factory are claimed to have a median breaking strength of 200 tons. For a random sample of 9 rods, the breaking strengths measured in tons are as follows. The scientist believes that the median breaking strength of the metal rods produced by the factory is less than 200 tons. Use a Wilcoxon sign rank test at 5% significance level to test whether there is evidence to support the scientist's belief. Okay, so first of all, H null always says that the median is equal to whatever is stated. Okay, which means that H null is equal to, no wait, we write in colon. H null is that the median, the population median, is equal to 200. Remember, whatever value stated here, H null always says that the median is equal to this for any kind of non-parametric test. And then we have H1, which states the scientist's belief, or whatever belief is being made usually. Scientist believes that the median is less than 200. So that means M, the population median M, is lower than 200. These are our two hypotheses. Next up, we need to do, okay, so I'm going to label all these values as X. Okay, so now we're going to have a different, whenever we have a stated median value, in this case 200 tons, we have to use a certain thing called X minus our median value here, X minus M, and where M is equal to 200. But M is equal to 200 as stated as in the hypothesis. You can write X minus 200, that is no issues either. So when we do X minus M, you're gonna get different values for each. So when you do for the first one, 210 minus 200 gives you a positive 10 value. Moving on, we have 186 minus 200, which gives you negative 14. Now these values are easy to subtract, so there is no need for the usage of a calculator. 208 minus 200 is just going to be that 3, then this will be negative 16. The following will be negative 9, positive 15, negative 2, and negative 4. This is what we call X minus M. Now we need to rank them. Okay, so what's the smallest value when you disregard the signs? Okay, let's just disregard the signs for a moment and find out the smallest value. And that's going to be this one right here, 1. We're going to label this from numbers 1 to 9 because there are 9 samples. Okay, we're going to label each number in ascending order with 1 to 9. Okay, so this is going to be 1. The next value is going to be 4 over here, that's 2. Remember, just ignore the signs. Next one is going to be the 8 here, which becomes 3. Next we have we have here 4. We will have here 5. Right. We will have over here rank of 5. Next up we will have negative 12, so it's 6. This will be 7, 8, 9. Okay, now since it's called a signed rank test, it obviously means that there's going to be a lot of usage of sign. Now we're going to correspondingly put the negative values for each value that's below. Negative 14 means negative 7 is your rank. Negative 12 means negative 6 is the rank. Positive 8 means positive 3 is the rank. and negative 16 means negative 9, negative 9 means negative 4, positive 15 gives 8, negative 2, negative 1, negative 4, negative 2. This is just basically what we need to do. Okay, now comes a tricky part that people sometimes mess up, the positive values. So now we have to add up every single positive value we have here, which is 5, 3, 8. That they are all the positive values we have. When you add them up together, we get 16. And now for the negative values, Q, we represent them in the letter Q. So right, let's add up all the negative values. Let's disregard the signs. Okay, we take the absolute value of it. So 7 plus 6 is 13, 13 plus 9 is 22, 22 plus 4 is 26, 26 plus 1, 27, and this is negative 29. So 29 totally. 29. Our test statistic, which is represented in letters T, let's write this as a formula. So T is equal to the minimum of P comma Q, which is equal to the minimum. What's the minimum value here, P or Q? 16 or 29? It's going to be 16. So this is our test statistic, 16. Okay, next we have to just state the number of samples, which is equal to 9. And next we have to state whether if it's a single tail test and at what percent are we looking at. In this case it is a single tail test because we are looking at every median that is below 200, not above, not equal to, below. So it's a single tail test. We're not looking on the higher side, only the lower side. So it's a single tail test at 5% significance level, which means if you convert 5% to decimal, you get 0.05 at one tail. Okay, using the data right here, we get, okay, yeah, we have to go to this thing right here. For a single tail test of 0.05 and a sample size of 9, our critical value becomes 8. So we can write over here that critical value from tabular column is 8. Okay, so this just states our critical value, and now we're coming to the conclusions. So now we have to compare the test statistic and the critical value. This is there for every single test, no matter what. 16 is a test statistic and critical value is 8. You can clearly see that 16 is greater than 8. So normally when the test statistic is greater than the critical value, we reject it. But given that this is a non-parametric test, it means that we accept H null. So we accept H null. Okay. When we accept H null, there is a structure that we must follow, and that is saying there is insufficient evidence, and then we state out H1, which is the population median being lesser than 200, or we can say to support the scientist's belief. So insufficient evidence to support the scientist's belief, and that is how we write our answer. Okay, yeah. The second part is, why is Wilcoxon sign rank test preferable to a sign test when both are valid? So what a sign test does is that it looks at every value that is above and every value that is below the value 200 in this case. So that means that this would have a negative, this would have negative, sorry, this would be having a positive value, this is a negative, negative, positive, negative, negative, positive, negative, negative. You can see that they don't look at the magnitude of the difference. They don't look at how far you are away from the median, right? So then after that they just do S plus, which is the total number of values that are greater than the median, is going to be 3, and then they're going to do a binomial approximation for this. While this may be a little accurate, it's not as accurate as taking into consideration how far you are away from the median. For all as I know that 201 and 210 still fall under positive values. which means despite having a difference of 9, they still fall in the same category, which is obviously going to alter the test statistic. So here we can write the magnitude of difference from stated median is not taken into consideration in a sign test, unlike the Wilcoxon signed rank test. Right, so this would be how you should write the answer. Yeah, that should sum up the second question as well. Third question, this is a goodness of fit test, and this falls under chi squared test. So this is important whenever you have goodness of fit test. Okay, and 5% significance level, total sample of 150 bags and sold in bags of 5. This is a tricky statement because they're expecting you to multiply based reading on the question, saying that probability of it weighing more than 100 grams is 0.35. Then other apples in the bag. There are a random sample of 150 bags, which means that your sample is going to be 150. It's not going to be 150 times 5, because this is just going to be used to trick you. Do not fall for it. When they say that the random sample of 150 bags, it means that the sample size n is equal to 150. You shouldn't have any more confusion. This is all that you need. Okay, now from now we should know that it says that the probability of an apple weighing more than 100 grams is 0.35. That means that let's consider the probability of an apple weighing more than 100 grams as a success. If an apple weighs more than 100 grams, we call it success. If an apple weighs lesser than 100 grams, we call it failure, right? Okay, so the probability of success is 0.35, and that is denoted with the letter P. The probability of a failure would be 1 minus P, which is Q. Right. Okay, yes. So now that we have the main values here, you should know that whenever we have success and failure, we are going to deal with the binomial approximation or binomial expansion. So we need to use the binomial approximation for this. We can go to the list of formula, which comes in really handy when you don't remember all these total, and we'll have to use combinations. Okay, so nr pr p to power r, and then 1 minus p, which is represented as q, and minus r. Okay, when I say n is the total sample size, okay, so this is the total sample size. You don't want to take this as the value n in our exponents, so let's take this as we will take this as y. Oh no, we will take this as f. Okay, we're going to call that the frequency, I guess. Instead of this being f, we'll take this as f. Okay, so now we should know that a certain formula for this is the binomial expansion. It says that it's nr multiplied by 0.35, which is p to power r, multiplied by 0.65 to the power n minus r. So now how do we do this? Okay, let's first create a table where we have here x0, yeah, have here x0, 1, 2, 3, 4, 5. So this is just the x values, and this is going to be our the next row is going to be the binomial probability. So binomial prob. Okay, now how do we get the binomial probability? Very simple. So we just need to plug in these values. To use combinations, this right here, we have to first use over here our n value. Our n value will be the topmost value of x, which is 5. Do be confused? Do not be confused. That is, don't count each of these number of x values. That is 6. 6 is not going to be your n value. It's going to be the maximum value here, which is 5. 5, and then you put shift division that shows C. 5CR, R being the current value you are on, which is 0. 0. Multiply this with 0.35 to the power of R, R being 0, multiplied by 0.65 to the power of n minus R, which is 5 minus 0, which is just to the power of 5. And this is equal to 0.116029, which is, we can represent this into 5 significant figures. So let me write this in text. 0.11603. This is the binomial probability for the first one when x equals 0. Similarly, we repeat this for the next one as well. So when r equals 1, we can replace all the zeros here with 1, and n minus r becomes 5 minus 1, which is 4, and our binomial probability becomes 0.31238. Right, so let's write that down. Yeah, okay. Yes, okay. Next we need to plug in the value of 2. When r equals 2, we have here 5 combination 2 and 5 minus 2, which is 3. This has 0.33642. What was the previous value? 0.31239. My bad. 9. Okay, next up we have when the value of r equals to 3, which means that 5C3, and over here we have 2 power 3, over here we have 2, and our binomial probability for when r equals 3 is equal to 0.1811 and 5. Now when r equals 4, we can write over here 5 minus 4 is just 1, and to the power r will be just to the power of 4, and 5 combination 4 will give us the binomial probability of 0.04877. 0.04877. And finally, when r equals 5, we get over here 5 minus 5, which is 0, and over here to the power of 5, over here we have 5 combination 5, which is equal to, okay, a very very low value, which is 0.0525. 525. Fine, we'll keep it 5 decimal places for each. Okay, now what we need to do right here is that we need to observe and find out our expected values. How do we do these expected values, you may ask? So it's just multiplying our binomial probability with 150, which is our sample size here. So I'm going to write here E. Okay, and yeah, I'm going to put 0.11603 times 150, which is equal to this value here. We'll keep it to 3. You can keep it to, yeah, we think we can keep it to 5 decimal places, so we can have it like 17.405. But then again, our value isn't entirely accurate, so I would suggest doing the entire thing again. We can just put 5 combination 0 times 0.35 to the power 0 times 0.65 to the power 5. This should give our value, yeah, it should be more accurate, so times 150, and this gives us 17.404. Yeah, this is a more accurate value which you should use. I think I will write this as well in text just to make it a bit more visible. 17.404. Right. So for the next one, we can get back to a binomial. Okay, now we have over here when it's to power 4, and over here, and doing this we should get our probability of 0.31239. So using this, we multiply it with 150, we get 46.86 or 858. Yeah, that we can keep it to 5 significant figures, so 46.858. Right, so for now we have this value. We can move on and put our third value here. It's a bit tedious applying each and every value into this, but it is also less error prone. So let's do this here. We should get our 0.33642, and we multiply that with our sample size 150. Our expected value becomes 50.462. So 50.462, and we go back to our equation. We have here to power 2, this becomes to power 3. So what we're doing is just repeating to get each of the binomial value probabilities. It would be easier to just calculate the binomial probability and then do the expected value, and then go back, put it in the formula and find the expected, which would have been much more efficient. And we get here 27.172. 7.172. We have now next power 1. This is to the power 4, and now we do 5 combination 4, and our probability becomes this, and we multiply it with 150. Our probability comes 7.3155. So we're going to put this as 7.3155, and the final one we have here, we can completely disregard that. The power 5, and this is multiplied with 150. We get the value 0.7878. Okay, 0.7878. Okay, now what you should know is that before we calculate our summation values, our test statistic using summation formulas, you should know that the summation formulas do not hold for expected values below 5. Over here we do have an expected value below 5, so we cannot proceed just yet. How do we remove this issue? Is that we need to add this to our next value, which is 4 over here. In doing so, we will get all values above 5. So let's add this with 7.3155, 8.103, 8.10332, okay. So we have 8.103, then we have here 27.172, 50.462, 46.858, and finally we have 17.404. Right. Now how do we proceed from this using the formula that's used in almost every chi-square test? So there's a summation formula where we need to calculate our test statistic. It will be our observed value minus our expected value, whole square that difference and divide it with our expected value. Okay, and then we repeat this for all. So basically we have to use the summation. Okay, where I equals to 1 and n is the maximum number of sample size, which is still 5. I. So this is our entire formula. Using this formula you can get our values. So we have here observed value of, we have an observed value for the first one as 12. We subtract that with our expected value of 17.04. 0.404. We whole square the difference. It doesn't matter which order you do this in, because we are whole squaring that difference. So we get either a positive or negative value for the difference, and then when you whole square that, the value becomes positive anyway, so you need not worry about that. Plus, okay, let's write that down in the calculator. 12 minus, no wait, 12 minus 17.404, whole square that and put 17.404 here. Right, and that's our first value. We need to calculate the second one as well, and the third, fourth, fifth, and sixth. Now when the first observed value is now 39, so 39 minus 46.858, and we subtract, and now that we've subtracted that from our observed value, we can just whole square the difference. We'll divide that with our expected value of 46.858, and now this may seem a little too tedious. I understand this. It's because that it's a binomial distribution problem, so our value is going to be much more difficult to calculate because of how many decimal places it has and its inability to be expressed as a fraction. So moving on, we have here the next one. We don't need a big bracket here. We can write in our calculator 39 minus 46.858 whole square divided by 46.858. Add that up with our next values. Our observed value for the second one is 46, so let's put in 46 here. Our expected value, however, is 50.462. We find the difference, we whole square it, and then we whole divide that with our expected value we've had, and that is this here. Now we add that on with when I equals to 4. Now when I equals 3. I equals 3, our expected value becomes 37. Right, so before I progress with the last one, I'm going to just plug in the values for the two we just did. Okay. We add this with 37 minus 27.172 the whole square divided by 27.72. Then finally we have the last one. Remember, we don't consider this because it is below 5 and hence our formula would not work. So please do not consider this when solving, and we only consider the new calculated frequency right here. So we have here, we have over here the next one, which is going to be observed value. What is our observed value? Now that we've combined this, our new column heading here becomes 4 and greater. Okay, so it becomes 4 and greater, or like 4 to 5. 4 to 5. It wouldn't matter what heading you do, whatever it is, given that you've merged the two columns. Now we have to merge the two observed frequencies. So 12 plus 4 equals to 16, and therefore our observed frequency is 16. Our expected frequency is going to be 8.103, and like before, we whole square the difference and whole divided by our expected value, and doing all this will give you our test statistic t. So before we get the t value, we need to put this in the calculator. And our final answer is 14.64. Keep it to 4 significant figures, because when we are comparing it to the statistical tables as shown over here in the chi-square test distribution, over here our statistical tables, they're going to be all in 4 significant figures. So let's keep it in 4 significant figures. Next, we need to find the critical value. So for the critical value, there are a few things that need to be considered when we're doing a goodness of fit test with the binomial approximation. First of all, we don't do the number of x values minus 1, and that is because we would get an incorrect degree of freedom, because we considered our expected value as a combination of the last two columns, which means that our total degrees, that means that total number of terms considered for the expected value is 5, and therefore degree of freedom equals to total number of terms considered for expected value 5 minus 1, which is equal to 4. Okay, so over here we have our row, and at 5% significance level, we just need to do 1 minus 5%, which is 1 minus 0.05, which means p equals to 0.95. In case you don't know how to solve this, you can just do 1 minus alpha, where alpha is 5%, and that gives us 9.488 as our critical value. How do we reference this as a critical value? Very simple. So we write here x squared like that, and we put like this. Next, we have to write our degree of freedom, which was 4, and then we need to write in brackets our probability, which is 0.95, and this is equal to 9.488. Oh, wait, we don't need that. Yes. And finally, now the last step of every single test is to actually compare the test statistic 14.64 in this case with our critical value, which is 9.488. And you can see over here. Alright, so before we do this, let's state our hypothesis. Okay, once again, not needed for these papers, but given that these are old, they don't require hypothesis for chi-square test. The newer papers, however, do. So our hypothesis would be first of all support Freya's claim. So the first hypothesis would state that data fits bin 5, 0.35 distribution. Yeah, wait, no, this says this what bin 5 comma 0.35 is a good fit. This is what Freya is claiming, 0.35. That is what it basically means. And over here it would mean that bin 5 comma 0.35 is not a good fit. This will be stated as our H1, which is our alternative hypothesis. So over here we can see that our test statistic is greater than our critical value, which means that we reject H null. Reject H null. When you reject H null, we have a sentence structure. There is insufficient evidence to support the alternative hypothesis. So there is sufficient evidence to state that or in this case we can say that to state there's sufficient evidence to reject Freya's claim. That's one way to frame a conclusion. We need some degrees of uncertainty, so yeah. Okay, next up we have here inferential statistics, and we can look through differences. Fine. Members of the Sprints Athletics Club has been taking part on an intense training scheme aimed at reducing their times to run at 400 meters. For a random sample of 9 athletes from the club, the times taken in seconds before and after the training scheme are given in the following table. Okay, the organizer of the training scheme says that on average an athlete's time will be reduced by 0.3 seconds. Test at the 10% significance level whether the organizer's claim is justified, stating any assumptions that you make. Fine. So whenever we talk about before and after, whenever we compare two different things like matched pairs, we have to always state that we assume that the population differences are normally distributed. This is like a constant all throughout using the t-test. This is essential. Without this, our entire thing falls apart. Okay, next up we need to state our hypothesis, and this is very important, especially in inferential statistics. So our null hypothesis would mean that there is no difference. Oh no, there is a difference of 0.3. He says that there will be a difference of 0.3 and it will be lesser than 0.3, which means that mean x minus mean y will be equal to 0.3. The difference between the two means will be equal to 0.3, and his claim is that difference between the two means, mean x minus mean y, will be reduced by more than 3 seconds, at least 0.3. So that means that have here greater than equal to, because it says that he will reduce by at least 0.3 seconds. Okay, moving on, we need to find the differences, because now we know that they are normally distributed. Differences are normally distributed. We need to calculate the difference. So 48.8 minus 47.9, that's what we're going to do, before minus after. So we get 0.9 for the first one. 48.2 minus 47.8 gives 0.4, which is the second one. 50.3 divided minus 49.6 gives 0.7. 49.6 minus 49.1 is 0.5. 49.4, so this is going to be negative 0.2. Remember, we have to take into considerations of the signs, and I'll tell you why. This has no difference at all. This one decreases by 0.1. This one also 1.2, and finally we have 0.3. Okay, now when we have these kind of values, we need to form our own values to find S2 of D. So the summation of all differences is equal to 0.9 plus 0.4 plus 0.7, 0.5 minus 0.2 plus 0 plus negative 0.1 plus 1.2 plus 0.3, and this gives us 3.7. So our summation of d values is 3.7. To find the summation of d squared would mean to square up every number and then add them. So is it meaning that 3.7 whole squared? That is incorrect. What this means is that we're going to be squaring each number individually. So 0.3 squared, 1.2 squared, and over here we disregard any kind of signs. We just add and add. So 0.1 the whole squared, because negative 0.1 the whole squared is the same as 0.1 the whole squared, so it wouldn't matter. And lastly we have this here is equal to 3.29. So we found our sum of d squared. Now we need to find the sample mean of d, which is number of the total sum 3.7 divided by number of samples, which is 3.7 divided by 9. So we have here 0.7 by 9, which is equal to 0.41 recurring. So it's equal to, our fractional form will be 37 over 90, but our real form that we're going to be specifying in our sheet will be 0.411. Okay, moving on, we need to find S2 of D, and we don't need to write D below. That is because we're not using two or more variables. We already have our values here, and this can be found using the same formula as we do before. So number of differences minus 1 whole multiplied by sum of d squared minus the sum of d the whole squared divided by number of d terms. This right here is going to give us the answer for S2. And now we just need to put this into the calculator. So number of samples were 8, so 9, so our denominator becomes 1 by 8. Sum d squared was 3.7. No wait, 3.29. We minus that with 3.7 the whole square divided by number of d terms, which was 9, and this is equal to 199 over 900, which is 0.221 whole recurring. Yeah, so we'll write here 199 over equal to 0.2211. Fine. Now that we have S2 of D, now we just need to find the final calculations. So to find our test statistic, T is equal to, first of all we write it as T, we don't write Z. The reason so is because we have a quantifiable one, 9 athletes, and this is visible in our T distribution critical values. Hence we have here T is equal to the sample mean or the difference mean, which is D here, minus it with 0.3, our stated mean, whole divided by root of S2 divided by number of terms. I'll put this in as ND, but it wouldn't matter. And so we can just write number of D mean was 37 by 90, and we subtract that with 0.3, whole divide that with the root of our answer as we calculated before by 9. which is equal to 0.70888. So 0.709. This is our test statistic. Now to find degrees of freedom. Degree of freedom would be number of samples minus 1, which is equal to 9 minus 1, which is equal to 8. P is equal to, now it says that it specifically leans towards one side of this entire test, which means that it's a one-tailed test. So we have to look here for a one-tailed test of 10% significance level. Okay. X minus mean y, freedom 8. Yes. Okay. So we have here 10 significance level for a one-tailed test. So it will be 1 minus alpha. Alpha being 10%. 10% is 0.1. So 1 minus 0.1 is equal to 0.9. So now that we have our p values and our nu, which is Greek letter, we go to degree of freedom 8 and 0.9, which is 1.397 as a critical value. So how to write this? It will be t comma 8 comma 0.90, and this is equal to our critical value, which is 1.397. Finally, we have the very statement that we need to write. So 0.708, we have that test statistic, and we have a critical value. Over here we have to compare between these two. Our critical value is greater, so whenever our critical value is greater in inferential statistics based questions or chi-square based questions, we accept H null. Okay, we accept the null hypothesis. But what that means is that we're going against the organizer's claim, right? So what that means is that we are saying it is insufficient, or there is insufficient evidence to support the organizer's claim. We don't say there is no, because we need uncertainty. Fine. Now that we've calculated that, we need to go to do PGF, probability generating functions. So just for quick understanding, when you have two unbiased coins, our probability of getting a heads is 1 by 2, and the probability of getting a tails is also 1 by 2. So yes, number of heads is by x. So find the probability generating function of x. So the probability of getting 0 heads would be 1 by 2 whole squared, because we're getting tails 2 times. So 1 by 2 times 1 by 2, 1 by 4. Probability of getting at least one head would be 1 by 2 times 1 by 2 times 2, which is going to be 1 by 2. It's quite weird, but it is rather simple when you think about it. 2 heads. Probability of getting 2 heads is the same as getting as 0 heads, which is 2 tails. That is going to be 1 by 4. And so now a t is associated with whatever number is written over here. So t will be to the power of 0 here, t will be to the power of 1 here, and t will be to the power of 2 here. Hence our final equation will be in that g x of t equals to 1 by 4 plus 1 by 2t plus 1 by 4t squared. This is our values, and if you want to, we're gonna probably be using to combine it. Yes, we'll be combining the two functions. So whenever we get the question to find the PGF, I would always suggest factorizing it. So when you factorize 1 by 4 out of this, you get 1 plus 2t plus t squared. This step is not important at all, but it is good if you do this step, because this makes the next few steps in the questions much easier. However, we can leave our final answer in this form. Okay, so Hassan has 3 coins, 2 of which are biased. So the probability of obtaining a head when tossed is 1 by 3. The probability of obtaining the head for the third coin is 1 by 4. Number of heads obtained by Hassan is when he tosses these 3 coins is denoted by y. Find the probability generated of y. So when you have 3 coins, the maximum number of heads you can get is 3. The minimum number of heads you can get is 0. So the probability of getting 0 heads. So given that the probability of obtaining a head is 1 by 3, the probability of not obtaining a head will be 2 by 3. And this goes for 2 coins, so 2 by 3 times 2 by 3. And the probability of not obtaining a head for the third coin is going to be 1 minus 1 by 4, which is 3 by 4. This is going to be 1 by 3. So we have here 1 by 3. Okay, now the probability of obtaining at least one head. So we're going to assume that we are going to not get head for the first 2 of them, which is 2 by 3 multiplied by 2 by 3 multiplied by, this time we're going to assume that we get a head. Okay, and this is the probability of getting a head in the third coin, and we can get this head in the second or the first one as well. So we multiply this entire value with 3. Right. So one head, just to be certain of this. Wait, actually instead of multiplying by 3, I think we should calculate. So we get 1 by 9 there and times it by getting a success in this one, which is by 3 multiplied by 3 by 4 plus this with getting a success in the first one and multiplying this with failure and failure. We get here 4 over 9. Yeah, that is not the same as the first one. The only reason we don't multiply with 3 in the first one is because the probability is now changing to a denominator of 4. So that was where I could have made a mistake. So it's good that I didn't. And now to find it for 2 heads, the entire probability. So it's going to maybe take some time. So what I would like to do is get to 3 heads immediately. Okay, so let's go to 3 heads right now. Probability getting a head in the first one is 1 by 3. Same thing goes for the second coin as well. And for the third coin, it's actually 1 by 4. You get here 1 by 36. So how do we calculate the probability to get 2 heads? It's simple. All the probabilities combined will give 1. Therefore, that means that 1 minus 1 by 36 minus 4 by 9 minus 1 by 3. This should give us the probability of getting 2 heads, which is 7 by 36. And so we can write our function g y t equals to 1 by 3, once again t to the power of 0. So we're not going to be having any value of there because it's just multiplied by 1. This will be 4 by 9 multiplied by t to the power 1, which is just t. 7 by 36 t squared plus 1 by 36 t cubed. And that is our gy of t function. Next, they're asking us to combine, as I've said before, to find the total number of heads obtained by CAIE and Hassan. The PGF of obtaining total number of heads is this, and total number of heads to get this is here. So before we combine it, we should know something, which is gz of t in this case is equal to gxt multiplied by gy of t. Right, so this is one thing that you must know. So when you're doing this, it's better you factorize. And so when you factorize 1 by 36 of this entire thing, you can get here 12 plus 16t, 16t, right? Yeah, plus 7t squared plus t cubed. It's gonna make your process whole the more easier. So gx of t is going to be 1 by 4 times 1 plus 2 times 1 plus 2t plus t squared, and this is multiplied by 1 by 36 of this right here. Right, so now how do we multiply this? Well, this is the basic algebra that we can just use. So 36 times 4 is equal to 1 by 44, 1 by 144. So that right here. And now we have to use the FOIL method. Very simple. 1 times all of these values will just give us all the values again. 70 squared. I think this looks a lot like putting two t's, so I'm going to just plus. Yeah. Okay, this is added when you have 2t multiplied with everything. So 2t times 12 is 24t. 2t times 16t is going to be 32t squared. Just gonna verify it. Yeah, it is. 2t times 7t squared equals 14t cubed. Cubed. And finally 2t times t cubed equals to 2t to the power 4. Moving on, we have the FOIL method with the last one, t squared. So we get here 12 times t squared equals 12t squared. Next we have here 16 times 16t squared is equal to 16t cubed plus 7t squared times t squared, which is going to be 7t to the power 4. And lastly t to the power 5. And this is our entire value here. Fine. Now we just need to combine this. So we have here gx of t as 12 plus 16t here, 24t here, which is going to be totally up to 40t. So I'm going to write here 40t. And coefficients of t squared sum up to 7t squared plus 32t squared, which is totally 39t squared. 39t squared plus 12 equals to 51t squared. And finally, no wait, not finally, then t cubed plus 14t cubed gives 15t cubed plus 16t cubed equals to 31t cubed. We have here 31t to the power 4. Next we have plus 2t to the power 4, 7t to the power 4, which is 9t to the power of 4, and this is added with t to the power 5. So this is your gx of t. Use the probability generating function z to find ez. So there's a formula to find the expected value of any probability generating function, which is ez is equal to will be the differentiate when t equals to 1. So how do we, first of all we need to manage to differentiate our PGF. Once again, this is the basics of math. You can differentiate this very simple. So gz differentiate t equals to, let's differentiate. So our constant here remains as 1 by 144, and over here when you differentiate 12 it becomes 0. When you differentiate t it becomes 40t, it becomes 40. This will become 51 times 2, which is 102t. 4 times 31 is going to be sorry, that it's not 4 times, that is going to be 3. Yeah, 3 times 31 equals to 93. Square. Note that all the exponents decrease by 1. T to the power 3. Finally 5 t to the power 4. This is our PGF of z when differentiated. Now we plug in the value at t equals to 1. So we get 1 by 144 of, we get 40 plus 102. It doesn't matter what degree of the polynomial t is in. Either way is 1 squared, 1 cubed, 1 to the power 4 is all going to be the same value of 1. So all we're doing is just adding up the coefficients of t and its polynomial terms. So doing the math here, 40 plus 102 plus 93, 36 and 5. We get 276 over 144. This is equal to 23 over 12. But expected values, they expect in 3 significant figures, so let's write this 1.92. This is our expected value. Finally, find the most probable value of z. So using the PGF right here, you can see to find the most probable value of z, we have to look at the coefficient with the highest coefficient over here. Okay, so let's assume that this is t to the power 0 as well. Okay, what is the highest coefficient of all these? It's going to be the 51 right here. 51 is tied to t to the power 2, which means our most probable value would be 2. So we can just write 2. That's literally it. Okay, finally we have here continuous random variables. Fine. Find the interquartile range of x. So the interquartile range is when you plug in fu, where u represents the upper quartile, minus fl, where fl represents lower quartile. This is our interquartile range. So how do we calculate fu? Fu will be equal to the 75th percentile. So that means that the function that we have over here, okay, will be equal to 3 by 4. So 1 by 60 times 16x minus x squared equals to 3 by 4. Now we can multiply 60 on both sides. We get but before we do this, we have to know that it's not x squared now, it's going to be 16u and u squared. Reason we put u is because we're plugging in each value of x with u. 16u minus u squared equals to 45. And now I would like my polynomial with the highest degree as positive, so I'm going to put this in as u squared minus 16u plus 45. Essentially all I did was just bring all the terms to the right, and this will be equating to 0. Okay, and now instead of using the quadratics formula, we can just go to this. It will show equation slash function, and over here we're going to go for polynomial with degree 2, and we just enter our coefficients. We have 8 plus root 19, 8 minus root 19. Which one do we choose? The range is between 0 to 6, so 8 plus root 19 gives 12.35. 8 minus root 19, however, gives 3.64, which is within range. So our value of u equals to 8 minus root 19. Do note we don't need it in decimal forms just yet. Okay, this is because we are using it still in our calculations. They're not saying to calculate upper quartile. Okay, moving on. F of L, basically the lower quartile. Let's take this in different ink to avoid confusion. Yes, F of L. So that means that 1 by 60 16L minus 16L squared is equal to, lower quartile is the 25th percentile, which is represented as 1 by 4 in fractions. We multiply 16 both sides, you get 16L minus L squared equals to 15. Okay, and now we can put our L squared in positive coefficients, so L squared minus 16L plus 15 equals to 0. We can factorize if you want. Can we factorize for this case? Yeah, we could factorize for this one, but we don't really need to. And so let's put this in our calculator. So 1 minus 16, 15. So L could be equal to 15 or L could be equal to 1. Which one do we use? Since 1 is within range of 0 to 6 and 15 isn't, we take L equals 1. Equals to 1. So now that we have our values for U and L, we're just going to do, oh by the way, this is going to be U minus L. That is the interquartile range. So that's going to be 8 minus root 19 minus 1, which is finally equal to 7 minus root 19. But they're not asking us to solve an exact form, so they expect 3 significant figures. So we can just go to our calculator, put this in 3 significant figures, and we have here 2.64. Fine, that is E of x. Now to find E of x cubed when we have a CDF, it would mean first to differentiate. So let's do dy of dx. No, actually it's going to be d of dx. Just differentiate d of dx, and the constant was 1 by 60, so we can factorize that out, and we have here 16x minus x squared. When you differentiate this, we will be getting we're gonna get 1 by 60 times 16 minus 2x. Okay, so now that we have this already, now we just need to differentiate. No, we need to integrate, but this time we need to multiply x cubed to our entire thing. So now we need to go back to integrating this thing with the limits. Okay, our limits is 6 to 0. So now let's multiply x cubed. We get 16x cubed here, minus it with 2x times x cubed, which is 2x to the power 4. And yes, and we've not integrated just yet. All we've done is just put the limits and just multiply the entire thing by x cubed. Now we need to integrate, and this part may be a little bit tricky, but shouldn't be much of a challenge. So 16x cubed, how do we integrate that? It's going to be 4x to the power 4, 4x to the power 4, and this is subtracted with 2 by 5 x to the power 5. Right. Okay, moving on, we have the limits 6 and 0. So when we plug in our upper and lower limits, you will see that when you plug in 0, it has no effect on the overall solution. So now we just need to plug in our upper limit. It will be 4 times 6 to the power 4 minus 2 by 5 multiplied by 6 to the power 5. Okay, and using this we can calculate 1 by 60 multiplied by 4 times 6 to the power 4, and this is subtracted from 2 by 5, times 6 to power 5, and then we'll close the bracket, and we should get here 34.56. Right, but given that the values are exact, I think we can leave in this figure, but we can keep it at 3 significant figures. If we get an exact value, it's better we state it in like exact. And I think this is the last question. Yeah, find the PDF of y such that when y equals to root x. So we have over here in our entire CDF x and x. We don't have root x anywhere, so we need to convert x equals to y squared, because when you square both sides you get x equals y squared. This is the first step. So in our function we have 1 by 60 times 16x minus 6x squared. So over here when you plug in values of this, you just need to do 1 by 16, that's 16 y squared minus y to power 4. This is essentially the CDF when you replace with y. And this is for what range exactly? From 0 to 6. 0 x 6. But remember that now we are replacing our value of x with y squared. So that means we put here y squared. So let's solve these inequalities separately. When 0 is lesser than or equal to y squared, it means that y is greater than or equal to 0. That's the first part. And y squared being lesser than or equal to 6, which means that y is lesser than or equal to the positive root of 6. Therefore our range of y will become this right here. This is our range of y. So let's just cut down on the working a little bit, and we'll just put this as our range. Just cut it out, and we have here, just need to add the root and remove the exponent. Okay, now that we've done that, this isn't it just yet. We need to find the PDF of y, which means even if we found the g function of y, we write it as g, not f. Now that we found the g function, we need to find smaller case g y. How do we do this? Is going to be simple, just normal differentiation. So 1 by 60 multiplied it with differentiation of 16y squared is equal to 32y. Differentiation of y to power 4 is just 4y to power 3, and that's pretty much it. And we need to specify the range, so 0 y root 6. Okay, and in every PDF you have to state in PDF you need to write 0 otherwise, 0 otherwise. So it's important that you write the last step, because this usually counts for a mark as well. And that should be it for all of the probability statistics of the winter series October-November of 2020. This is of the QP41, which is the same as QP43. I hope you enjoyed this video, and I hope you like, share and subscribe, and see you until next time. So goodbye.